Hello there, this is Dr. Dixon, and we are going to do some equilibrium practice problems. So let's get right into it here. So the first one we are going to do says write the equilibrium constant expression and calculate the equilibrium constant for the reaction below with the following concentrations. And so since they don't say anything else about this, you can assume that those are equilibrium concentrations. They didn't say they were initial concentrations. So let's start off with writing the equilibrium constant expression itself. It's going to be products over reactants. Since all three of these have concentrations, we'll assume that they're all aqueous here. They all participate in the equilibrium reaction here. So again, when we write an equilibrium constant, or if you're writing a Q expression, it's products over reactants. So here the SO3 is the only product. So we'll put SO3 in the numerator, and then that 2 right there needs to go in as an exponent. Remember, any coefficients in your balanced equation become exponents in the equilibrium constant expression. So there's our numerator, and then both reactant species will go in the denominator. So the SO2 will go in here. That's also going to get squared because of that 2 in the balanced equation. And then that's multiplied. You don't add them in the equilibrium constant expression. You multiply them by the concentration here of O2. There's only one O2 here, so we don't need to write anything for that. All right, so that's how you write the equilibrium constant expression for that reaction. And then it's just a matter of plugging in the given concentrations that we have there. So the SO3, the 5 times 10 to the minus 2, goes in the numerator. We could also write that as 5.0. Again, we're going to square that in the numerator, and then the SO2 goes in the denominator. That's going to be 0.0030. That one gets squared also. And then multiplied. I'm just converting those scientific notation numbers into regular numbers. And then the O2 is also in the denominator, 0.0035 for that one. All right. And then from there, it's a matter of just doing the math. And I did these earlier. That comes out to 7.9 times 10 to the 4th power for that one. So pretty big K value then. That's going to indicate that this is a very product favored system just based on those concentrations. You can also see the reactant equilibrium concentrations are pretty tiny, about more than 10 times smaller than the product concentration. So that results in a pretty large K value then for this. All right, so that's how we do that first one. And so then the next one's related to that same one. It says determine K if the reaction were reversed. So in other words, if we had 2SO3 as the reactant and then the 2SO2 and the O2 as the products. And so there, basically, essentially just flips the equilibrium constant expression top to bottom. We'll have the SO2 and the O2 in the numerator, and then the SO3 squared in the denominator. And since we just figured that out in the previous problem, all you need to do, you don't even need to really write it out. When you reverse a reaction, you can simply take the reciprocal of the equilibrium constant. So in other words, 1 over that 7.9 10 to the 4th value that we just did. And so that comes out to, if you just plug that in on your calculator, it comes out to 1.3 times 10 to the minus 5th power. That's the K value for the reverse reaction. All right, so if you reverse a reaction, you take the reciprocal of that K value. All right, so pretty straightforward there. Next, for the reaction, 2NO plus O2 goes to 2NO2, where everything's in the gas phase. If the equilibrium constant in terms of concentration is 6.9 10 to the 5th power at 227 degrees Celsius, what is the value of Kp at this temperature? And they gave us this nice equation over here that relates Kp and Kc together. They are related through the RT and a delta N. They're actually related through the ideal gas law, PV equals nRT. The value for R is this 0.0821. The units on that are liters, atmospheres over moles Kelvin. You don't really need that for this problem, but those are the units for this. And so what we're going to do is just plug in everything that we know about this system. So we're trying to solve for that Kp value. We're given the Kc value. That's the 6.9 10 to the 5th power. And then we're going to multiply R and T together. So the R value is the 0.0821. We're going to multiply that by T. The big thing you've got to remember with this equation, though, is the temperature must be on the Kelvin temperature scale. So we're going to take 227 degrees Celsius. We're going to add to that 273. That's how we convert Celsius into Kelvin. And so that actually comes out to 500 Kelvin. So that's what we're going to plug in down here is our 500 Kelvin value. Now, the other thing we got to look at is this exponent, this delta N exponent. Delta N is the change in moles of gas. And how you find delta N, just write it down here. Delta N is the moles of gaseous product minus the moles of gaseous reactant. There we go. And so you just need to get those from the balanced equation itself. Just look at the coefficients. And so add up all of the product gas coefficients. In this case, there's only one product gas. That is the 2 moles of NO2. So we're going to use 2 for the moles of gaseous product. Then we're going to subtract from that the moles of gaseous reactant, which there's 2 moles of NO and 1 mole of O2. So that's 3 moles of gaseous reactant. And so then the delta N value here is a -1. So we're going to raise that 0.0821 times 500 value. If we just multiply those together, I had that here, it's 41.05. If you multiply those together, and then we're going to raise that to the negative first power. So our answer will take 6.9, 10 to the fifth power, and we're going to multiply that. Again, it's 41.05 to the negative first power. That is 0.02436. And when you do the math on that, it comes out to 1.7 10 to the fourth power. And there's our answer for that. All right, so that's how you do that particular problem. Next one, the equilibrium constant, Kc, for the reaction below is 6.9 10 to the fifth power. This looks familiar. It's the same one we just looked at. A 5-liter reaction vessel at 500 Kelvin, same temperature, was filled with 0.06 moles of NO, 1 mole of O2, and 0.8 moles of NO2. Calculate QC for this reaction. All right, so QC is the reaction quotient in terms of concentration. So remember, Q works exactly the same way as K. In terms of the setup for that, here it's going to be the NO2 concentration squared over the NO concentration, also squared, times the O2. Just go back to that first problem. Again, why those two things are squared is because of those 2's in the balanced equation. And so then from here, we need to plug in concentration. Now, you got to be a little bit careful with this one. They did not give us concentration amounts. They gave us mole amounts of those things. So we need to take each of those concentration amounts and mole amounts and convert them into concentration. So to find the concentration of NO, we're going to take the moles of NO and we divide it by the volume that we were given. It's that 5-liter amount right there. And so we'll do that for all 3 of these. So we'll get the concentration of O2 here as well. And that's the 1 mole divided by the same volume. These are all in the same volume. So that's all going to be the same for every single one of these. And then the last one, the NO2, was 0.8 moles. And again, divide by 5 liters there. And so we can get each of those. The first one here comes out to 0.012 moles per liter. The second one is 0.20 moles per liter. And the last one is 0.16 moles per liter. All right, so anytime you go to plug into a Q expression or a K expression, you got to make sure you have those in terms of concentration. Now it's just a matter of plugging everything in. So we have the 0.16. We're going to square that in the numerator. The 0.012 goes in the denominator, and that one's also squared. And then the O2 is just 0.20. And so if we do the math on that, that comes out to 889. For that. So that's our Q value. That by itself doesn't tell you a whole lot, but it tells us we got a lot more product than reactant at this current moment in time. But we can now answer this next question. Is the reaction mixture at equilibrium? And to determine that, we're going to compare the Q value versus the K value. And so the Q value here is 889. The K value, on the other hand, is really big. It is 690,000. So that means Q is much, much smaller than K. When Q is too small compared to your K value, that means you've got too much reactant in the system. that's not at equilibrium. If they're equal to each other, then they are at equilibrium. But in this case, whenever Q is less than K, that means you've got more reactant than you're supposed to have at equilibrium. So to get to equilibrium, this equilibrium needs to shift to make more product. In other words, we say it shifts to the right. All right, we're going to decrease those reactant concentrations. We'll use up some of the 0.012. We use up some of the 0.2 molar, and we need to increase then that product concentration. All right, but they didn't ask us to figure that part out. They just wanted to know which way will it shift. And so this one will shift towards the products for that net direction. All right, so really good test question there. You'll see something very similar to that in your exam coming up in a couple of weeks. All right, next, here's another reaction where they give us some initial amounts. We've got 1 mole of CS2, 5 moles of Cl2 placed into a container and allowed to come to equilibrium. So those first amounts are not equilibrium amounts. Those are starting amounts or initial amounts. The mixture is then found to contain 0.45 moles of CCl4. How many moles of Cl2 are present at equilibrium? So when you see this kind of a problem where they give you some starting amounts, they might give you an equilibrium amount, they might give you a change amount, any of those types of things, you're going to want to set up an ICE table, right? Or where ICE stands for initial, change, and equilibrium. We went through an example like this in the lecture material as well. So in this case, you have 1 mole of the CS2 and 5 moles of the Cl2. And the nice thing about ICE calculations, you can actually do those in moles or you can do them in terms of concentration. When you do them in concentration, you got to make sure, though, everything's in the same container, all mixed together. If they're not, then it's actually easier to work in moles. So we got those initial amounts there. They don't tell us anything about the initial amounts of our 2 products, so we will start those out at 0 then. All right, and then as far as the change is concerned, since these 2 are 0, they've got nowhere to go but up. They have to increase. Remember, your mole amounts or concentrations cannot be negative. So if anything's starting at 0, it has to increase. The other thing I'll remind you of is if the products are increasing, then that automatically means the reactants have to decrease. All right, reactants and products will always change opposite each other. All right, so if one side's increasing, the other side has to be decreasing. Then we'll put this in terms of X. Since this is an equilibrium, we don't know what the change in X is going to be. So it'll just be a 1X decrease for the CS2 because there's only one equivalent of CS2. For the Cl2, however, it's going to be a decrease of 3X because of the 3 there in the balanced equation. And then just 1 each of the 2 products, those will both increase by X. And so then just combine the initial and the change lines together, and you'll get your equilibrium line. And of course, 0 plus X is just X for each of those. Now go back to the information you're given and see what else we can relate. So they said at equilibrium, it's found to contain 0.45 moles of this CCl4. So what we called X, we can now say that that's equal to 0.45 moles. And so wherever we find X, it's going to be equal to that 0.45 then. So for example, right here, we know we're going to have 0.45 moles of S2Cl2. And over here, we can take 1 minus 0.45, and that will give us, where's my answer to that? It's on another page. That gives me 55 moles of CS2 in this. The one thing they asked about, they want to know how many moles of Cl2. And so here, we're going to take 5 minus 3 times 0.45, since X is equal to 0.45. And when you do the math there, you get 3.65 moles of Cl2 for this. And so there's our answer. All right, so again, a lot of times it makes it really easy. You don't always have to plug everything into an equilibrium constant expression. All right, let's try the next one here. It says, assume that the change in pressure of H2S is small enough to be neglected in the following problem. We use this technique pretty often, especially if the algebra is going to get kind of out of hand or very difficult to solve. And so we'll do a number of examples, especially as we go into the acid-base chapter, where we do this approximation trick. But in this case, they're saying it's okay or should be okay to neglect the change in H2S. So they want us to calculate the equilibrium pressures of all the species in the equilibrium mixture that results from this decomposition. So again, we're going to do one of our ice calculations. So they give us the initial pressure, and we're going to do all this in pressures in this case. Initial pressure, the only thing we've got is that initial pressure of H2S. So once again, we can assume that the initial pressures of the two products are both going to be 0. As the reaction goes to equilibrium, then those two have no choice. They have to go up. Again, you can't have a negative pressure of a substance. You can have a pressure that decreases, but you won't have a negative value for its absolute pressure in that case, just like the same issue for moles. And if the products are increasing, that means the reactant has to decrease. So we can go ahead and do our typical ice calculation here. Again, these both change by 2x because of the 2's in front of them in the balanced equation, and then just a 1x for the S2. So at equilibrium, we would expect to get 0.824 minus 2x for that pressure, and then 2x for the H2, and x for the S2 amounts. Now, the equilibrium constant expression, we can do that in terms of partial pressures here. It'd be the partial pressure of H2 at equilibrium. Just like concentration, we square the partial pressure when there's a 2 in front of that substance in the equilibrium or in the balanced equation. And then the partial pressure of S2, that's just to the first power. And then the denominator is the partial pressure of H2S, and we would square that one. All right, so that's our setup for the equilibrium constant expression. Now, let's go back to this part where they're talking about it being neglected. In other words, what they're saying is the change in H2S is so small that we can effectively ignore it, that 2x is really close to 0. All right, it's not 0, but they're assuming it's really, really close to 0, or at the very least, much smaller than 0.824. So when we subtract it, it doesn't affect it a whole lot. So in other words, we're just going to approximate the equilibrium amount of H2S as 0.824 atmospheres. And then we'll have our 2x and x in there. So now we can go ahead and plug everything in. 2.2 10 to the minus 6 goes in for the Kp value. The H2 concentration at equilibrium we set is equal to 2x. We're going to square that, again, because of that squared right there. Multiply that by the partial pressure of S2. That's just x. And then the denominator, we're going to not use 0.824 minus 2x, but just 0.824. And then again, we have to square that according to our equilibrium constant expression. If we didn't, that would make this a lot more difficult to solve, because we'd have an x cubed term, as you'll see in just a second, and an x squared term and an x term potentially, and it would be very, very difficult to solve. With this approximation, this makes this a lot easier to figure out. So when I square the denominator here, I get 0.679. I did that right here. Let me double check that. 0.824 squared. Yep, it's 0.678976. I'll round it off to 0.679 for that. And so now I just multiply 0.679 by the 2.2 10 to the minus 6. That cancels it out on this side. And so when I do that on the left-hand side here, I get 3.73 10 to the minus 7. On the right-hand side, so let me write this up here. 2x squared, what that is 2x times 2x, or in other words, 4x squared. And then I still have to multiply it by that x over there. So when I do all of that, I get 4x cubed. All right, so 2x times 2x, that's what I'm doing when I take 2x squared. That's how I got this 4x squared. And then times the third x over here, that's where I got 4x cubed. Now I can divide both sides by 4. And when I do that, actually, that is the, sorry about that. That is this 3.73 10 to the minus 7. I didn't write out the, let me do that real quick. 0.679 times 2.2 10 to the minus 6. That would have been 1.49 10 to the minus 6. There we go. And then that I divided by 4 to get this number here. So when we cancel out the 4's there, x cubed is equal to this 3.73 10 to the minus 3. And I made some notes before I actually did this. And now what we're going to do is take the cube root, or raise that to the 1/3 power. So when we do that, we get an x value of 7.20, 10 to the minus 3. All right, so that's our value for x. Now we can bring that all the way back up here, plug it in here, plug it in here. We could even plug it back into the original equilibrium amount for H2S and get our approximate new H2S partial pressure. So if we go down the list here, the partial pressure of H2S, we would expect that to be 0.824 minus 2 times the 7.20, 10 to the minus 3. And that comes out to, again, this is an approximate value, 0.810 for that. And then we'll do the same thing for the pressure of H2. We don't square it here. We square it when we're plugging it into the equilibrium constant expression. But here it's just the plain old concentration of that, or partial pressure rather, in this case. So we'll take the 7.2, 10 to the minus 3 and double that to get that atmospheric pressure, 0.0144 atmospheres there. These are all in atmospheres when you do this in partial pressures. And finally, the partial pressure of S2, the last one here, that's just straight up X in this case. And so that is the 7.2, 10 to the minus 3, or you could also write it as 0.0072. And that was the atmosphere pressure there of S2. This one was H2, and this is H2S. And so those are your answers for that particular one. All right, I think that was my last one in this set. So if you have any questions about that, contact your instructor, whether it's me or somebody else. And otherwise, thanks for watching.